Namaskar. Welcome to the sessions on food technology. In this session, we are understanding the drying and incineration process. Drying and incineration are thermal processes employed in several food industries. Drying, in general, is used to increase the shelf life of the prepared food and even employed in solid waste management. Incineration is considered as a best method and only option for removal of few solid wastes. Let us understand both the topics in this session in the following headings. The first being the evaporation, drying, thermal conversion, incineration, cleaning out flue gas and solidify outputs. The first topic, the evaporation. Evaporation is a method used to concentrate non-steam volatile wastewater components. The evaporation plant contains a vapor condenser by which vapor and steam volatile compounds are separated from the concentrate. While the concentrate is then recycled into the evaporator, the exhaust steam can be used for indirect heating of other evaporator stages. The degree of concentration of the wastewater components depends on the different factors. For example, reuse of the concentrate, example, reuse in production, use as fodder, recovery of recyclable material, type of disposal of the concentrate, example, incineration, landfill, properties of the concentrate, example, viscosity, propensity to form incrustation, chemical stability. Advantages of this method include the residue can be reused as fodder and fertilizer. Only a small area is needed. Exhaust steam can be reused as energy. Considered state of the art in the food industry. Disadvantages of this method is the exhaust steam from evaporation is organically polluted and needs treatment, rather high operation and maintenance costs. Drying. Drying of a food material occurs when water vapor is removed from its surface into the surrounding space, resulting in a relatively dried form of the material. Drying differs from the dewatering process. In dewatering, liquid water is drained or squeezed out of the material, but during drying, the heat can be supplied in different ways: convection, radiation, conduction, microwave, radio frequency, or even Joule heating. The principle of drying, no matter what drying mechanisms are involved, can be generally expressed by the following surface vapor flux equation: N_V is equal to Hm dot Pv dot S minus Pv dot infinity, where N_V is the vapor flux measured in kg per meter square per second, Hm is the mass transfer coefficient measured in meter per second, Pv, S is the interfacial vapor pressure at the moist material surface measured in kg per meter, and Pv, infinity is the vapor concentration in the surrounding space that vapor travels into measured in kg per meter cube. Hm is determined by the flow field around the material being dried meter per second, which may be viewed as a velocity of mass movement. When this vapor concentration difference is positive, vapor leaves the material and thus drying occurs. The reverse is the wetting humidification process. The drying process as a whole has to involve the generation of vapor transforming from the liquid phase into the moist material to gaseous phase on and within the moist material being dried and the transport of the water phases towards outside of the material. Some debates are around how liquid water may move within the material structure. The microstructure of the food materials is particularly relevant to drying, as both liquid water and water vapor move within the structure. The microstructure, as far as the transport of heat and chemical species is concerned, is mainly made up of compounds such as protein, fat, carbohydrate, minerals and air. Porosity and tortuosity are usual characteristics. The material's composition and its affinity to water play a key role in water holding capacity and local evaporation rates. Drying also creates a new microstructure as it progresses, and the spatial distribution of the microstructure characteristics, density included, is important in texture perception of the product and affects how it may be used as an ingredient for mixing into other foods. For instance, the reconstitution properties for food powders created by spray drying. For instance, microencapsulation is employed to protect the active and beneficial ingredients such as probiotic bacteria during drying. Drying is also preferably done at the lowest temperature possible for the same purpose of achieving higher retention of bioactivity. Bacterial cells or microorganisms are vulnerable in the drying process, especially when a high temperature environment is encountered. Drying may be viewed as a thermal processing stage. On the other hand, as mentioned above, preservation of the activities of the good beneficial bacteria such as probiotic bacteria becomes important when the drying process can be detrimental. There has been much research effort spent on understanding the fundamentals of drying and more complicated mathematical models published in the literature, but a concise introduction of drying still centers on the notion of three drying stages: a warming up bar cooling down period, a constant rate drying period, and a falling rate drying period. The maintenance of the constant drying rate period may be due to two reasons. One is the increasing temperature at the air product interface, that is increasing the interfacial vapor concentration even though the relative humidity might have gone below unity. The other is due to the material's surface nature, where relative humidity can be kept constant for quite a long time. There have been a large number of studies published in the past 2 decades on the drying of food and biological materials. In particular, the Page model appears to be the one that is the most successful in describing the weight loss versus time data obtained in a constant environment for drying. Let us understand what is thermal conversion. The thermal conversion of solid waste includes transformation of wastes into gaseous, liquid and solid conversion products. The process also generates energy due to burning of waste materials. Thermal processing also results in waste volume reduction. Combustion or incineration, pyrolysis and gasification techniques are the techniques employed for thermal conversion. A waste treatment technology which includes the combustion of waste for the recovering energy is called as incineration. Incineration coupled with high temperature waste treatments are recognized as thermal treatments. During the process of incineration, the waste material that is treated is converted into gases, particles and heat. These products are later used for generation of electricity. The gases, flue gases are the first treated for eradication of pollutants before going into atmosphere. Thermal treatment. In spite of the wide range of approaches to waste treatment in food sector, in some cases thermal treatment is the most effective or the only one applicable. Compared to other disposal methods, it has a number of advantages such as short time of treatment. In case of landfilling, it may take decades for the waste to decompose. Another one is the possibility of treating hazardous waste, as for example in the case of animal carcasses contaminated by dangerous contagious microorganisms, possibility of off-gas control, abatement of environmental impacts, possibility of utilizing heat released by the oxidation process, that is waste to energy. The thermal treatment may be used for wide spectrum of waste from solid to gaseous. The choice of suitable thermal treatment technology is then based on the type of treated waste and its characteristic properties. Examples described below include completely different technologies applicable to different type of waste. Incineration of solid residues with relatively low water content and free of hazardous properties may be performed in units very similar to biomass boilers. A typical example is provided by peach and olive pits. Due to the character of this waste, it is not necessary to equip the units with complicated flue gas cleaning systems. Another example of solid waste is sludge, namely wastewater treatment plant sludge. In contrast to the latter example, high water content may be expected, thus requiring completely different approach and technologies. One possibility is sludge co-firing after drying. One suitable process is cement and burned lime production, where an alternate fuel can be fed using a special feeder directly into rotary kiln. In some cases, however, it is necessary to apply special sludge incineration technology. This is very often based on a multiple earth combustion chamber. For hazardous waste like some types of meat and bone meal, thermal treatment is the only alternative. In such cases, systems based on a rotary kiln and secondary combustion chamber is preferred. Let us understand the incineration. Incineration as a disposal method involves burning the trash. Sometimes this is simply referred to as thermal treatment, as a general category of high temperature treatment of trash material. This method can be used to transform waste into heat, gas, steam and ash. One of the advantages of the incineration is that with this method, refuse volume can be reduced by half or more, or it requires little usage of land. An incineration facility can be built in a small area to process huge amounts of waste. It definitely saves a lot of space compared with using a landfill only. This method is popular in countries like Japan, where space is a limitation. Incineration of waste materials converts the waste into ash, flue gas and heat. The ash is mostly formed by the inorganic constituents of the waste and may take the form of solid lumps or particulates carried by the flue gas. Some incinerators generate energy from the burning of waste. These plants are called waste to energy plants. Incinerators reduce the volume of waste by about 90% and weight by 75%. There are 8 types of incinerators: fixed earth incinerators, rotary kiln, plasma arc, liquid injection, fluidized bed, multiple earth, catalytic combustor and static earth incinerators. In 1885, the US Army created the first garbage incinerator in the New York Harbour. Let us understand these types of incinerators. Let us understand the first one, rotary kiln. The rotary kiln Hearth system has been used for several hundred years in the pyroprocessing industry. The rotary kiln concept accomplishes 2 objectives simultaneously: moving solids into and out of a high temperature combustion zone and mixing and stoking the solids during combustion. In its classical embodiment, a kiln is comprised of a steel cylindrical shell lined with abrasion resistant refractory to prevent overheating of the metal. A kiln is generally inclined slightly toward the discharge end, and the movement of the solids being processed is controlled by the speed of the rotation. In some instances, special provisions have been made for air cooling or water cooling the kiln shell, thus eliminating the use of refractory. For example, a steel kiln cooled with external water sprays known as the Lance converter was developed by pyrolysis application in the mid 1960s. In the later 1970s, a new kiln technology emerged involving a water-cooled kiln cylinder fabricated of steel boiler tubes welded together and manifolded for the introduction of feed water and withdrawal of steam. The other one is the plasma gasification. Plasma gasification is another form of waste management. Plasma is primarily an electrically charged or a highly ionized gas. Lighting is one type of plasma which produces temperatures that exceeds 12,600 degree Fahrenheit. With this method of waste disposal, a vessel uses characteristic plasma torches operating at plus 10,000 degree Fahrenheit, which is creating a gasification zone till 3000 degree Fahrenheit for the conversion of solid or liquid wastes into a syngas. During the treatment solid waste by plasma gasification, the waste molecular bonds are broken down as a result of the intense heat in the vessels and the elemental components. Thanks to this process, destruction of waste and dangerous materials is found. This form of waste disposal provides renewable energy and an assortment of other fantastic benefits. Plasma or incinerators ionize inert gases via an electric arc between 2 electrodes. This plasma creates an extraordinary amount of heat ranging from 3000 to 7000 degrees Celsius. The extreme heat can easily break down organic compounds into their basic atoms, which later recombine to form gases such as carbon dioxide. Inorganic material is left as a stable, leach resistant slag. Concerns surrounding plasma are incineration, including ensuring that gas emissions are minimal and clean before being released to the atmosphere. The another type is the fluid bed systems. The fluid bed system, incineration systems relative to bubbling fluid bed, applications in burning biological wastewater sludge and circulating fluid bed applications in burning hazardous wastes are widely employed. These two waste management areas were the dominant applications of fluid bed technology in the United States at the beginning of the 1990s, but several applications for municipal solid waste could be found in Japan and Europe. In order to provide a feed bed with relatively homogeneous composition and size, almost all solid waste fired in bubbling fluid bed or circulating fluid bed units are pre-processed or at least made somewhat more homogeneous through waste separation at the point of generation. Both bubbling fluid bed or circulating fluid bed furnaces can accept other fuels such as wood chips, coal or chipped tires. By acquiring these relatively clean alternate energy sources when the prices are favorable, energy revenues can sometimes be increased significantly with little increase in maintenance and operating cost. The other type is the stationary hearth system. Those incinerator furnace systems that operate without grates include the stationary hearth, rotary hearth and rotary kiln. The stationary hearth is usually a refractory floor to the furnace, which may have openings for the admission of air under slight pressure below the burning material on the earth, in the manner of the blacksmith's forge. In the absence of under fire air ports, air is admitted along the sides or from the top of the furnace and combustion proceeds in the same surface burning manner as in the bonfire, but with improved condition due to the re-radiation of the heat from the surrounding furnace walls and roof. Unless the refuse being processed provides a porous burning mass, it is necessary to provide manual stocking with slice bars to stir the mass of refuse in order to achieve a reasonable burning rate and degree of burnout. Stationary hearth furnaces are used for most commercial and smaller industrial incinerators. They are also used almost exclusively in crematories and for hospital wastes. For the latter applications, auxiliary gas or oil burners are used to maintain the furnace temperature in the range of 650 degree to 900 degree centigrade in the presence of adequate quantities of oxygen from air, well dispersed throughout the gas. In burning such high moisture waste, primary chamber burners are needed to ensure complete oxidation of combustible solids and vapors for the elimination of smoke and odors. Confident smoke and odor control requires auxiliary fuel burners under automatic temperature control in a secondary combustion chamber. The another type is moving grate system. The incinerator plant used for treating municipal solid waste is moving grate. This grate is capable of hauling waste from combustion chamber to give way to complete and effective combustion. A single such plant is capable of taking a 35 metric tons of waste every hour for treatment. Moving grates are more precisely known as incinerators of municipal solid waste. This waste is poured in the grate with the help of a crane. From here, the waste has to move towards the ash pit. Waste is further treated and waterlogs wash out ash from it. Air is then flown through the waste and this blown air works for cooling down the grate. Some of grates are cooled with the help of water. Air is blown through the boiler for another time, but this time comparatively faster than before. This air helps in complete burning of the flue gases with the introduction of turmoil leading to better mixing and excess of oxygen. In some grades, the combustion air at fast speed is blown in separate chamber. European Waste Incineration Directive is of the view that an incineration plant must be designed so that operating worker must know that flue gases are reaching the temperature of 850 degree centigrade within 2 seconds. This would ensure complete and required breakdown of toxins of organic nature. In order to achieve this, every time backup auxiliary burners must be installed. We need to have a system analysis for the successful incineration process. The basic information used in the analysis of combustion systems can include tabulated thermochemical data, the results of the several varieties of laboratory and field analysis, and basic rate data. Guiding the use of these data are fundamental relations that prescribe the combining proportions in the molecules and those that indicate the course and heat effect of chemical reactions. The last being the cleaning out flue gas and solidify outputs. A number of processes are involved for the cleaning up of flue gas. The mixture of flue gas is collected by means of particle filtration, and this filtration is conducted using electrostatic precipitators and baghouse filters. Baghouse are very effective for fine particles. The next step of the processing and cleaning of the flue gas is processing of scrubbers, which are critical for the removal of hydrochloric acid, nitric acid, mercury, hydrofluoric acid, lead and residuary heavy metals. With the reaction of lime, sulfur is converted into gypsum. The wastewater which comes out of the scrubbers is then passed through wastewater treatment plant. Desulfurization is a process that is used to remove sulfur dioxide with the limestone slurry injection directly into the flue gas. The nitric components of gases are reduced with catalytic reduction with the help of ammonia application. Heavy metals are removed with the help of active carbon injection. Particles are collected at the filters. So, what is the solidify outputs? Flue gas and bottom ash is produced with the processing of waste materials and settle at the bottom of the incineration plant. The ash which is produced is 4 to 5% of the total weight of the waste processed, while the flue ash makes up some 10 to 20% of total weight of waste material. The heavy metals which are contained in the flue or bottom ash are lead, cadmium, zinc and copper. A small amount of furans and dioxins are also produced. It is to mention here that bottom ash seldom have heavy metals in it. Flue ash is hazardous, while bottom ash is not that dangerous or injurious to health. In conclusion, the incineration is considered to be the best method of waste management over landfill, provided it helps in recovery of energy from the solid waste. Even though landfill is most commonly practiced form of waste management, its contribution to the pollution of groundwater and air through leachates and even huge requirements of land has made incineration most suitable for management of selected solid wastes. Thank you.